So at this time, I'd like to begin session 1 and call team 12 on AquaSense, who will talk about their project.
We're Team 12, AquaSense. My name's Marque, today, Malika, and Amil. And what the project is about is we have this school, the Carter School. It's a school for special needs children. And they have a water feature outside which has different bollards you press to make the water come out of various features. The issue they were having was there's a disconnect between the press the bollard and the water comes out of each feature. There's a short delay. And the children were having an issue connecting. You press a button, cause water to come out. So our job was to make a system which has a button which you press, makes an audible clicking sound. So students can recognize you press the button, the clicking sound goes on, as well as an LED system, which is going to have LED going from the bottom of the bollard all the way to the top. So they can see not only is there a sound, there's a light feature that goes on. So they're aware that the two things are connected.
Actually, a picture of the Carter School's sensory garden. You can see a couple of water features that they have there. The big, large green arch is the one that we're currently working on. And this here are the activation bollards. So basically that is what you press in order to activate the water features. You can see a couple more. There's just a water coming from the ground with something like an umbrella water feature. Some pictures of, we have like different water features there. Just a couple of pictures of, this one is also another water feature. Here's our level 0 block diagram that we came up with. We'll have the microcontroller. We'll have the magnetic sensor circuit connected to it, which is going to be installed on the arch itself. We'll have the LED strip, button interface, and button interface activated by pressing the button. Here's the dimensions of the water feature we're working on the board. The board is 29 feet, and the distance between the board and the arch is 3 feet.
Okay, so since the LEDs are turning on, we need something to tell them to turn off. So basically, how it's going to work is there's going to be a button. When you press that button, the LEDs are going to turn on and display a pattern. There's going to be a sensor which senses that the water's turned off. So basically, the sensor is in this diagonal flap here. And there's a ring around the arch, which is just a mount for that, and then there's this, the magnet is in the flap, and the sensor circuit is on the arch itself. So when water comes out of the exit hole, it's going to push away the flap. And the way the sensor works is, depending on how close the magnet is to it, the output voltage will be different. So in our case, the voltage will first be low, about 0.9 volts, and then when the flap is pulled away, it's going to be a high of 2.6 volts. So that is going to be sent to the microcontroller, which will tell the LEDs to turn off. This is the button we're using. So it makes the clicking sound, which is one of the things we wanted to do. And it has a receiver, which can receive from 30 feet. The output of the receiver is a switch. It's basically connected to a circuit, so when the button's pressed, the circuit outputs a low voltage. And that's also sent to the microcontroller to say turn on the LEDs. And this is what it looks like. So you can see the nut relay is going to be closed. It's going to have the microcontroller is going to receive a high voltage. I'm sorry, a low voltage.
The LEDs we chose to use were a programmable strip of LEDs. The LEDs are individually adjustable, so we can write to each one and have any pattern that we desire. They have 8 bits of color in them, so we can do anything from green, red, yellow, whatever we choose. We actually chose green because of the price we get with those LEDs. We're going to have 10 LEDs on at one time, given that this calculation right here shows how bright the LEDs are going to be. We saw it in the sunlight, it's bright enough for the children to see. That's a bit about the code that we had. We had a baseline sample code which showed us how to turn on just one LED or specific patterns, which we analyzed to figure out how to do our own patterns. We also had the code took in information from the Hall sensor, as Amil said, and parsed it using the ECE, so we could see when it's higher than 2.2 volts. So we could turn on and off the LEDs, as well as taking a high-low input from the button in order to turn on the LEDs.
This is the hardware schematic for the alarm system. The basic components include 2 voltage regulators, MSP430 microcontroller, a receiver that receives signal from the button, and we have LEDs here. For the physical setup, the system will be connected to 120 volts AC power outlet. 120 volts will be converted to 12 volts by an AC adapter that converts 120 volts to 12 volts, and then 12 volts will be converted to 3.3 volts by an 371 voltage regulator. This voltage will be used by the microcontroller and also another voltage regulator that converts 12 volts to 5 volts to be used by the sensor and LEDs. The receiver has its own, it's powered by AA batteries, so 3 volts, and there will be wired like that. And this is our PCB board. We have all our components wired together, but unfortunately, due to our design, one of the voltage regulators for outputting 5 volts instead of 3.3 volts, so that would burn the microcontroller, so we decided not to use it. However, for our demo, we will be using a breadboard to show the complete functioning of the alarm system. This is what we have here.
In order to install it actually in the cartridge bowl, we'll have to have something that will surround the casing of the board, with all the electronic components. So the casing is made of acrylic plastic. The height of the casing is going to be exactly as the height of the board in the cartridge spool, which is 36.5 inches. Each side is 9 inches. It is because we need and it's actually larger than the board itself, because we need like an extra spacing for the LEDs and the electric components to go inside. So acrylic is really good material for us to use because it's clear, it transmits all the visible light, it's weather resistant, it's not gonna be affected by the amount of water that is there in the cartridge spool. And we also added like a wooden support for it to stand more securely on the ground. The top of the casing is going to be spring-loaded with a stainless steel springs, which is going to be glued by the water-resistant, very strong glue. We're going to have the acrylic top with the aluminum sheet glued to it. We need an aluminum sheet to activate the board itself, and we're going to have our own button on top, which is going to activate the electronic components, like the LED pattern that we added. That's it for now. If you have any questions, we're ready to answer.
Just pulling up this slide here. Obviously, this casing is not designed to. It's designed to make things tamper-proof, not waterproof. So Obviously, there's going to be LEDs and electronics in there, so we don't want people to be able to tamper with them. So inside this casing, there's going to be another casing, which is actually watertight, which will hold all the electronics near the bottom of the receiver and pretty much everything else except the sensor.
Question?
What was the mistake that made the 5 volts instead of 3 volts? Did you discover what the error was?
No, we haven't yet.
Oh, okay.
Still trying to figure it out. But both the regulators are outputting too high voltage.
Have you thought about how you're going to run the wires to the Hall effect sensor of the water feature?
Yeah, that's good. We're gonna need to use maybe a dielectric spray to make them watertight. But like the big issue as well is running the power from the outlet. So we're gonna need to have a casing around the adapter and around that wire as well. And that's gonna be something that you have to be really careful about. You're gonna have to test carefully before we install anything because we've had a lot of bumps and stuff. So.
Would you consider using EMX or any other color control system to modulate LEDs?
No, I guess the only option that I thought of were using an Arduino or an SP430. Yeah.
Question? I thank you.